So good afternoon. Let's continue from where we basically left off last class. Basically we were trying to write down the Hermann-Morgen symbols for some pattern. Okay, so we were talking about the point group of that particular pattern. So we looked at this particular example last. So this was the example that was given to you, and we have to write the Hermann-Morgen symbol. So we agreed that there is a threefold rotation that is present. Once there is a threefold rotation present, we will start looking for mirrors that are basically having the equivalent A, B and C, or A1, A2, A3 as the normals. So in this case we clearly see that that is not there, right? That is not there. So we put a 1. Okay. The next slot will be for a mirror with these as the normals, right? With the ones that bisect these axes. So essentially the A1, A2, A3 axis themselves, there are normals along those axis, and we clearly see that it is present. Therefore the point group for this particular pattern is 3, 1m. This is what we saw. So when we put a 1 there, we say that there is no symmetry element associated with that slot. Basically there is no mirror associated with that slot. Previously we saw 6 mm and now we saw 3, 1m. Next, what about this particular pattern? What are the symmetry elements that you can identify when you look at this pattern? So there is a fourfold rotation, right? Once there is a fourfold rotation, it is natural for us to look at mirror planes. The next slot is for mirror planes with the equivalent A or the 1, 0 axis as the normal. So are they present here? Yes. So therefore we put a M in that slot. The next mirrors will have to have the diagonals as the normals. So do we have those mirrors now? Yes. So the point group associated with this pattern is 4 mm. Okay. Right now we are just looking at the symmetry of this pattern, or writing down the point group Hermann-Morgen symbol for this particular pattern. Later on we will see how this translates into becoming a plane group, okay, where you also have translational operators associated with the point group symbol. So this is 4 mm, we just saw that. What about this one? What can you say about the first thing that you want to look for is a rotation axis. So 6-fold rotation is present, right? Right here you have a in the center you have a 6-fold rotation. Once you look at the 6-fold rotation, what else should you have? You naturally want to think of the same set of mirrors, right? The same set of are there mirrors? No. Is the other mirror there? Basically, is A1, A2, A3 itself a mirror? No. So this is just 6. The point group of this pattern is just 6. Okay. So we saw point groups. Okay. Now when we include the possibility of translational symmetry, we increase the total number of possibilities. So when you say translational symmetry, there are two things that you can think of. One is basically the lattice translations along the vectors, and then we talked about one more translational symmetry operator when it comes to 2 dimensions, which was called as the glide plane. So essentially you have a reflection about a mirror and then movement of that reflected element by half the lattice distance of the lattice vector, okay, in a direction that is parallel to this mirror. So these are the two things that is interesting to us. So in 2D we don't have any other translational symmetry operator. However, in 3D, in addition to the glide planes, you will also have something called as screw rotation, which involves rotation and then moving by a certain amount in a direction along the axis of rotation. Okay. So the idea is so when you combine these point groups along with the various translational symmetry operators, you happen to get only 17 different possibilities. Therefore, we say that there are 17 plane groups. Okay. How many point groups were there? No, 5 Bravais lattices, 10 point groups in 2D. In 2D there are only 10 different point groups, which are basically generated by these mirrors and rotations. Now, if you want to study these 17 point groups, one way to do that is to actually placing the patterns over the various 5 different Bravais lattices. Now, these patterns can have some symmetry, right? And we know that the Bravais lattice itself has some symmetry associated with it. But when we combine the motif with some symmetry with a Bravais lattice which is probably having another symmetry, you will get an infinitely a pattern which is distributed in the two directions infinitely, and that distribution or that pattern need not necessarily be the pattern of the motif or the pattern of the underlying Bravais lattice. Okay. So let us take for example this particular pattern that I have generated. Okay, this particular pattern that I have generated. So the motif is of, what is the symmetry of the motif? Just 6 mm, right? 6 mm. What is the motif of the Bravais lattice? 2 mm. Okay, so you basically take 2 mm means just a rectangular lattice. Okay, and at each lattice point I am placing these things. So the symmetry of this pattern is not the symmetry of the motif. First thing that you should look at it is that the symmetry of the pattern is not the symmetry of the motif. However, in this case, the symmetry of the pattern is what? What symmetry does it have? Does it have the symmetry of the underlying Bravais lattice itself? 2 mm, does it have twofold rotation possible? Yes. Are there mirrors like that, and are there mirrors like that which are non-equivalent directions for the rectangular unit cell? Yes. So this pattern belongs to P2mm space group. So in this case, it so happened that the final space group of the entire pattern was actually the space group of the Bravais lattice, but we will see a couple of more examples where this is not the case, and we have to know how to identify them. So consider this one. This one I have placed 6. Okay, I have placed the motif with 6 as the point group, but I am using an underlying Bravais lattice 2 mm. Now if you look at it, it neither possesses 2 mm nor does it possess 6, and the only thing that it possesses is what does it possess? There is only a twofold rotation possible. That is the only symmetry that is there here, right? So this is belonging to the space group P2, and the point group of this entire thing would be, the point group of this entire symbol would be, entire pattern would be simply 2. Okay, if you remove the P there, you would get a 2. So generally, it so happens that the motif must at least possess the symmetry of the underlying Bravais lattice, so that the generated pattern does not lose the symmetry of the underlying Bravais lattice. Okay, this seems to be happening at least in the examples that we have looked at. Now let us consider this one. So consider the following Bravais pattern where you have a point, the pattern is that which is being put at all the lattice point is the only symmetry is M. The only thing is M. So we generally use a asymmetric pattern or asymmetric symbol to talk about various symmetry in whenever we are studying crystallography, to make our understanding clear. So we have taken this particular asymmetric unit and then reflected it like that, and then therefore this particular pattern has symmetry M. That is the only symmetry that is present here, and that is being combined with the Bravais lattice with 2 symmetry. Now the question is, what is the symmetry of the underlying pattern itself? What is the plane group? What is the plane group? It is definitely not 2, right? Because if you rotate it by 180 degrees, for example, if you think that there is a rotation axis by 180 degrees, and if you rotate it, you would not get this to look like that. You would rather get it to look with these longer edges on this side, right? It should look something like that, but it is not looking that way. So what is the symmetry here? Is there mirror? There are no mirrors. So what is the symmetry? 1. So in this case, combining this mirror with 2 produced a pattern where the only symmetry is 1. Okay. So in this manner, it's possible for you to identify or classify the various plane groups into 17 different categories. Now we talked about glide line. So this is a good description of what happens when you have a glide line or a glide plane, so to speak. So when you take this particular centered lattice, this is centered lattice, right? There is a lattice point here, there is a lattice point here, there is a lattice point here, and I am combining this motif which has the symmetry M along with the centered lattice. That is one of the centered Bravais lattice, right? So what are the various symmetry elements you can actually identify? So you can identify a glide line here, which essentially involves reflecting this element about this mirror to get this, and then moving it 1/2 a lattice vector. Similarly, this is also done the same way. For example, this particular motif may also be generated by reflecting this about this mirror and moving it this way, right, and so on. So everywhere through the infinite 2-dimensional lattice, you would have these glide lines present. Okay. So this introduces this glide line, but since this is present right in the center of the unit cell, we can use the C to talk about the centering. This is of course not primitive. Okay. Now it is not necessary that the centering, it is not necessary that when the glide reflection is present, that the new motif is always produced at the center of the unit cell. It could be located at other places as well. For example, let us take a look at this pattern. Okay, this pattern is having just a motif, and this motif has symmetry what? Now just 1, right? It has no other symmetry associated with it. But then what I am doing, I am reflecting it about this mirror and moving it half the distance. I am reflecting about this mirror right here, moving it half the distance, reflecting about this mirror here, moving it half the distance, and all these patterns have this feature. And it so happens that if this is the unit cell, this is not necessarily lying at the center, right? It's not lying at the center. So in this case, if you wanted to write the space group, okay, then first thing you would look at whether there is any rotational symmetry present. Are there any rotational symmetry present in this pattern? Can you identify 2-fold, 3-fold, 4-fold axis? So what would I put in that slot? 1. Okay. Are there any mirrors? See, there is the thing that a glide line is always present only in places where there is a mirror. Okay. So I will say that there is a glide line in a direction that is with normal as this axis, right, and then I look for glide lines with normal as this axis. Is that present? Is that present? No. So 1. Okay. If this is actually the P1G1 is actually the space group of this pattern, okay, and if I were to ask you to write down the point group of this pattern, what would you do? Point group involves removal of any translation related operations from the space group symbol. So this one has a P and this one also has a G. So I would just remove that and I would get 1 M1. I replace G with just the M. So this is the point group associated with just M, just M. Okay. So now you understand how we get a point group from a space group symbol. Yes? G. This G1. G1 is for the to see if there is any mirror that is perpendicular to it or in any other position. Nothing is there, you can just remove that, it's not required. There is only one G or one M, right? If I didn't move it, then the only thing that would be present is just the M. If I didn't translate it by that lattice vector after reflecting it, it would just be M, right? Yes or no? Any other question?
We don't, from reading the P1G, we don't know the actual translation for the G vector. I mean, we don't know the actual translation for the...
It's usually half the lattice vector. It's half the lattice vector, yes. Yes.
Sir, if we do not consider the glide after reflection, then I don't think we can say that mirror is also present in that.
Really? Okay, let us take a look. I don't know, I'll have to do it and see. So you say I'm just going to, this is the thing, then there should be one present here, right? Then there is one present here. So if there is one present here, there should also be one present here. So there should also be one present here, right? So is there a mirror? I think there's a mirror here and there's a mirror here.
But what is the initial structure?
No. The initial structure is the initial structure that I gave you now is this. But you are telling me that don't move it after reflecting it. Then the structure that is going to be generated is going to be different from this, right? That will look different. That will have only mirror. That won't have the glide. Yes. Is that clear? Can I move on? Any other questions?
Could you repeat about the normal, the light plane and its normal?
So we try to look at this pattern and try to figure out what symmetry elements are actually there. Okay, now that we have studied what a glide line is, which means reflection about some mirror plane and moving half the lattice vector in a direction that is parallel to the mirror. Okay, we see if something like that is actually present in this pattern. Okay, so for convenience I have actually marked the unit cell here. Usually, you can't, sometimes it can be hard to find that out. For convenience I have actually marked the unit cell that is present right here, and I look for, first thing that I look for whenever I am identifying symmetry is to see whether there is any rotation axis present. So in this case, is there any rotation present is the question that I would ask. Yes or no? No. There is no way I can rotate it by 1 yes, 2, 4, 3, 6 orders to actually get the same pattern again. So there is nothing. So I would not write, I would not put, so in that particular rotation slot I put 1 or don't write it at all. Then I see if there is any mirror. Okay, so naturally the mirror that I would like to look for is either along, in this case it's so obvious that the mirror is along this, the x-axis. The mirror is along the x-axis the mirror is along the x-axis, or its normal of the mirror is along the y-axis, right? Now what is x axis, what is y axis is all interchangeable. This is A and this is B, or this is A and this is B. It really doesn't matter in this case. You can simply interchange them. So if we want to stick to our original convention that the second slot should correspond to a mirror with normals as the A axis, then I would put 1 here. However, I would put a M here, because there are mirrors which are with y axis as a normal or with b axis as a normal, correct. However, this is not just a plain mirror in this case, right? It is not just a plain mirror, it is actually a glide plane. These mirrors are acting as a glide plane, so there is a reflection about this mirror, and then there is a movement of half the lattice vector. Half the lattice vector goes from this spot to this spot, right? By half the lattice vector it is being moved. It is being reflected about this mirror, and then by half the lattice vector it is being moved, and so on. It keeps going on and on, correct. So this is either 1G or 1G1 or just G. Anything would be fine. Okay, and I can use a primitive unit cell to actually generate this structure. The primitive unit cell will essentially contain it will contain, you know, this and this to basically generate it over and over again, correct. Will it get generated if I lattice translated in the x and the y directions? That is very important, right? It has to, simply by translating it in the x and the y direction, I should be able to generate the entire unit cell. What I am trying to get at is, it is not necessary for the glide reflections to always produce something at the center. It can look something like this as well, is what I am trying to emphasize. Is that clear? Yeah. Yes, M. What is that? When I?
When you are saying that it is mirror, you said that you will not include the translation when you are considering the translation.
Yes.
Right.
I am not considering glide reflections.
No, you are not considering glide reflection.
Glide reflections are also translations. They are not point groups. They are not point operate. They are not point symmetry operations.
No, like when you are saying, when you imply that it is mirror, you said that you will not translate.
We will not.
Apply the translation. When you said the point to symmetry is mirror.
Hmm.
Right, you said that we should not apply the translation when we are considering the point. Right, but you did it only for the top one but not the bottom part of the.
I didn't understand at all. I am not following your question at all. Anybody follow his question?
So, you do not account for both the glide planes,
Which one?
the top and
Yeah, I am not accounting. You are saying account for this glide plane separately from this glide plane.
No, at the same like when you said that we undo the translation.
We undo the translation. Yes.
When you are considering the point group.
Okay.
But you did it only for the top part of the motif, but not the bottom part of the motif.
So if I don't move it, what happens?
Either you move both of them or you don't move both of them.
If it is a glide plane, both have to be moved. That's it. If it is only a mirror, then it is only a mirror. It is not going to move.
Right.
Correct.
Both of them will not move, right? So
Yes, both of them will not move. So
you still not have the
this one gets reflected like this, right? So I am saying that there is a mirror here, there is a mirror here, right? So this will not be generated. This is not going to be generated. This will, again, you will have a thing here. This will not be generated. Now when I reflected about this, this will be generated, right? Yes or no? There is a mirror here means there is also a mirror here. There is no doubt about it, which means this will be generated and this is not going to be generated, and this will be generated. Correct? So what did I, is that right?
still not have mirror.
Where I don't have mirror? Where do I not have mirror? There is a mirror, right? There are mirrors, right?
So then why don't you make this mirror?
Where is the mirror? Show me the mirror there. There is no mirror. No, I can't. It's not there. If I put a mirror here like this, it would, how would it look? How would this scalene triangle look? If I put a mirror, it should look like this. It is not there. Correct. So
When we convert the space group to point group, how do you introduce a mirror group? Like why do you change that G to an X?
correct. That is a good question. So the question, the issue is because glide planes can exist only at spots where mirror exists. That's it. Glide planes exist only where mirror exists.
So we're just removing the translation.
That's it.
Like
That's
that
it.
and
Keeping them right. So you can generate a space group if you knew the point group by replacing all the m's with g's. All or some, depending upon what is available. For example, if you have 4mm, it means you can have a 4gm and so on, or you can have a 4mg, 4gg, but you will see that some of these things are essentially already there. They are going to repeat themselves if you draw it out and take a look at it. Okay, so people have done this work and given you a finite number of space groups that basically exist. Any other questions? Yeah.
When we say that it's a primitive, are we only looking at the tall half as one lattice, or
You could use a primitive unit cell to generate this structure.
but the way the rectangle is over there is it's still a primitive area?
What is that?
The way the rectangle has been drawn over there, will it still be a primitive?
Yeah, it is a primitive. So assume that this is a molecule with many atoms in it. These atoms are all placed about these lattice points in this manner. Okay, number of lattice points that are there inside this is number of lattice points, one lattice point is there. However, inside this unit cell I have different positions for these atoms. Which is what we will be looking at in next couple of slides. Okay, so by using these operations that we just discussed, basically the glide reflection, it is possible for you to generate these additional points as well. Okay, so this is just primitive unit cell is sufficient to generate this. Okay, you don't need a yeah.
In this unit cell, there are 4 corners, right?
4 corners are there.
So, if we are putting one motif at each corner, then
You can choose unit cells in any way you want. Choose any way you want.
so here it seems that in the top side I have put motifs in both the corners, but in the bottom one motif is one side plus it's two triangles.
This triangle and this part become one motive. No, I don't have two. I have just drawn it that way. Right? How many motives are there here? Actually, we have to look at it very carefully. Can these two motives be generated from just this? By take this, reflect it about this point and move it here. You can. Right? So let us come to that in a little bit. Okay, but the purpose of having this slide is just to tell you that the glide reflection need not produce centered lattices. That's it. Is that okay? Need not be always centered. It will be centered provided your mirror plane is passing at the appropriate locations. If it is passing right here, then it would get reflected like this, and you move half, you will get a centered lattice, but not otherwise. So I just have a couple of questions. This we have already seen this. This should be extremely easy as to find out what point group this pattern belongs to. So you should be able to find out the remaining point groups and draw their patterns. You should be able to easily find them We have seen, I think, 4 or 5 or 6 point groups already. Should be able to take a look at the others, and I want you to be able to draw these patterns. A good idea would be to use this scalene triangle and then apply various symmetry operators to generate those, using those various elements that may be present in those point groups. This is another pattern that I have given here. So you should be able to take a look at it and answer these questions. Is there a guide line? What is a space group? You have to think about it a little bit. It's not as obvious as some of the other ones. Okay, you might have to look at it carefully and write down what the space group is. This basically was generated with the 6 with the centered lattice, but what happens to it is something else. This one is a little bit more complicated. There's a, what is a motive? This is a motive, but it's flipped in different ways, right? And there are glide lines, there are mirrors, everything is there here, but it has got to be only one of those 17 different plane groups. So what is it? Okay, so these are the only different point groups possible, 17 different point groups. The Hermann-Maugeon symbol is right here for these 17 different point groups, and what is useful for us, in terms of being able to construct computational samples to do molecular dynamics simulations or so on and so forth, is what unit cell can be conveniently used in order to generate these patterns, in order to generate these space groups. So if it's P1 or P2, it is a parallelogram. Okay, it's PM, PG, CM, and there is a mirror, it becomes a rectangle, right? If it's PMM, again it's a rectangle. The rectangle, CMM is a rhombus, so CMM you can also use a rectangle. Okay, I will show you these plane groups in the next slide in a bit. The second you see a fourfold rotation being present, it is natural for us to think of a square unit cell. Okay, all these are square unit cells. If it has a threefold rotation or a sixfold rotation, it becomes a unit cell, hexagonal unit cell becomes a natural choice. So these things, if somebody were to give you this, tell you that some planar crystal is having the space group CMM, unless you actually knew that you could use rhombus or maybe even maybe a rectangle to generate this structure, it would not be possible for you to actually study it in more detail, right? So that's the main purpose of the first module of this course. We have to look at it even in 3D, right? We are not interested in 2D crystals, we want to look at 3-dimensional crystals. These are the 17 plane groups. Okay, these are not drawn by me, they have been obtained from this reference right here. It's freely available on the internet. This particular page has been reproduced from that. So all the various space groups are given here. Okay, this symbol indicates a twofold rotation. This symbol indicates the presence of a threefold rotation axis, fourfold, sixfold, and you can see the axis of reflection, axis of glide reflection. You have symbols for each of these various symmetry elements. So if you want to analyze this symbol, you need to look at this and see which of these things is applicable. So one of the most obvious things about this is it has what rotation? Fourfold rotation. So if it was a fourfold rotation, I would try to see if it is which of these three plane group would be appropriate. So these are all documented. The idea is to know how to read them and use them for our studies, for constructing the crystal structures and so on and so forth. Okay, so this is what I wanted to say. Now we'll come to the main aspect where if we want to describe a two-dimensional crystal, what can we do? What do we generally need? So we have somebody wants to construct a two-dimensional crystal. Okay, so draw it nicely. and the two-dimensional crystal is consisting of molecules of the following shape. It looks like there is a molecule like that. This is the molecule. That means there are several atoms constituting that molecule. Okay. And it is being repeated in two directions, and here you have the molecule looking like looking like that. This is the way the molecule, this is the way the unit cell looks, and it's being repeated in all the two directions. So one way to actually have somebody construct this on the computer would be to precisely define, say, fix a coordinate system here, say x, y, and then give the coordinates of all the atoms here, 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 and then repeat it in two dimensions. Just once you have the coordinates for one unit cell, you can simply repeat it in two dimensions. But sometimes these molecules don't just contain one atom or two atoms, they might be a big molecule, right? And every time it becomes hard for you to specify all the coordinates that is present in the unit cell. And at times you may have much more weird looking shapes for the molecules. This is an asymmetric molecule, it's not having any symmetry. But however, if I told you that this entire pattern, when it is getting repeated, belongs to the space group P4, okay, and I gave you only once the coordinates of all the atoms constituting this molecule with respect to, say, some coordinate system, okay, you should be able to generate the coordinates of all the other atoms computationally. Okay. So what that means, we will see what that means. Okay, we will take a look at, instead of looking at such a large molecule right at the beginning, so let us take our crystal which has 2D crystal which has P4, and so there is a fourfold symmetry passing through this point. Okay. I take an arbitrary general point x, y. Okay. This coordinate of this point is x, comma y. This entire lattice may or may not have the mirrors at this point, right? I have not said that it has, because it's just P4. So the only symmetry operator that is present is a fourfold rotation. Okay. So now what happens when I apply a fourfold rotation to this general point x, comma y? So the if you want to think of it as a rotation about the z, then the corresponding rotation matrix would be, right, which means theta is equal to pi by 2, right, 90 degrees. So this becomes 0, minus 1, 1, 0. So I first apply this rotation to the point x, comma y, and that will generate minus y, comma x, which means, so the x coordinate is actually minus y and the y coordinate is actually x, so it generates this point, right. If I now perform the same operation once again on this what do I get? Minus x minus y. So there is correspondingly a point somewhere here, and I apply the same fourfold rotation to this, I get a point somewhere, you know, like a square. So you can imagine it to be becoming a square like that, right. So the fourfold rotation, how many points does it generate? It generates 4 different points. So there is x comma y, there is minus y comma x, there is minus x comma minus y, and there will be one more, which is, what is that? Y comma minus x. Okay. Therefore, now each of these new points that have been generated are equivalent by symmetry. They are the same thing, just they have been obtained by rotating x comma y by applying this fourfold rotation to that, right. Once again, if you start doing it, it will start generating the same points again and again, right. When I applied this rotation matrix to x comma y, after the 4th time it starts repeating itself. So there are only 4 different points that it will generate when I apply this symmetry element. Therefore, the multiplicity is 4. Okay, the multiplicity is 4. Now this is a general point. That means it is not located on any of the symmetry elements that is actually present in this structure, right. So let us take, for example, suppose in P4 the P4 does not have any mirrors or anything like that, right. It just has a fourfold rotation. So suppose this point, the atom, what I talked about was x comma y was some atom in that asymmetric 6 type looking molecule. Okay, like this, because I know that the fourfold rotation generates for any given x comma y, it always generates minus y x minus y, y minus x. I will always know what points it will generate for any atom present in that molecule once I am able to give its x comma y coordinate. Okay. Now what happens if that one of the atoms is actually lying right on the fourfold rotation axis? How many new elements, how many new atoms will be generated if I perform fourfold rotations? Will it generate more? This atom will this atom get generated more number of times? However, this will right, this will get generated more number of times, this will generate more number of times, but the one that is located right on top of the symmetry element does not get generated more than once. It is already there, the thing that is given to you, the x comma y that is given to you. Such positions are called as special positions. And their multiplicity will be lower because applying P4 to that point doesn't generate anything new. Is that right? Yeah.
You cannot put any motive as special. Motive also must have symmetry.
No, I am not putting the motive itself. I am saying one atom that the motive is constituted of. Like, see, so this let us not take a 6 type, let us take a scalene triangle type molecule. This is our molecule. Okay. Each and every x comma y here will constitute a scaling triangle here, a scaling triangle here, and scaling triangle here on when I apply the fourfold rotation, and I can easily generate that by just applying this symmetry operators over and over again. Okay. Now, if it so happens that this molecule is not like this, it's like this. And I apply the fourfold rotation, this x comma y is lying on a symmetry point, a point through which a symmetry element is passing through. Consequently, the multiplicity of that point gets reduced, right? It is only 1 in this case. So, in this manner, you have two positions that are important when you are trying to generate these crystal structures. One is the general position, which will have the maximum multiplicity, and then special positions where the atom is actually lying on top of a symmetry element. We will see more of this in the subsequent classes. Okay. But what I would like to end this class with is for you to note the following. So, when you have x comma y here, you generated minus y comma x, then you generated another one, what is that, minus x comma minus y, and you generated y comma minus x, right? You generated 4 points by performing this P4 operation on a general point x comma y. Now, this is a lattice which is extending to infinity in the two directions. That means there is a unit cell to the left of it, there is unit cell to the right of it, there is unit cell to the bottom, and there is unit cell to the top. If there is an atom generated right here, it automatically means that there is an atom right here, right? If there is an atom here, it automatically means there is one right here. If there is an atom here, it automatically means there is one atom right here. Okay. Consequently, these are all fractional coordinates of the atoms. They are not the actual x, y, z coordinates. I should have mentioned that. They are the fractional coordinates of the atoms inside the unit cell. So, if you have, after you apply this operation, if you get minus y and x, all it means is there is an atom located inside the same unit cell with coordinate 1 minus y comma x. So, minus y translates to 1 minus y inside the unit cell, and 1 minus x translates to 1 minus x inside the same unit cell that you are looking at. So, once you generate all these points, you write a small script to generate all these points, you can automatically then use lattice translations to simply generate the entire crystal structure. So, you do not need people to give you all these coordinates. This generate, of course, it sometimes seems to be painstaking to generate even these 4 points by applying the fourfold rotation, but that has also been done to you depending upon the space group or the plane group that you are looking at. So, I will introduce that to you in the next class.